This video tutorial will cover the input and execution of a two-way slab with unbonded post-tensioning in ADAPT PTRC 2018. We're going to go ahead and we've launched the program, and we're going to select the post-tension option here versus the RC option. We'll say OK. And we're going to have three spans of 15 feet, 28.5 feet, and 30 feet. The tributary will be 260 inches, and then we're going to have an opening in span number 3. So if we go ahead and draw just a quick sketch of what we want to outline here, we're going to have a cantilever. This cantilever is 10 feet. Then we have a 30-foot span here, a 28.5 span, and then this span, this really isn't here, this span is 15 feet. Again, the cantilever is 10 feet. In this span, we have, if we look at a top view, we have a section that kind of looks like this. So this is the center line of the system, and then we basically have an opening here. So this dimension here will be 260 inches, and we're going to look at a 7-inch slab. Okay, so we'll model this. Let's go ahead and I'll delete that and then move this over to the side. We'll go ahead and select New. We'll set up a two-way slab system. This, we really need segmental input because we have to segment span number 3 because of the opening, so we'll select segmented option. We're not going to have any drop panels. This will just be a flat slab. We'll select Next. We're going to use ACI 318-2014. And then in the design settings, we'll leave these set as default. Execution mode, this really just allows us to interact with the recycler, so we can make modifications to the force or the profile. We want to have that ability. We're going to reduce moments to face of support for design, and we're going to leave redistribution off for now, and then we're going to use the equivalent frame method for the two-way slab analysis. Under the design options, we're going to disregard design capacity exceeding cracking moment. This does not apply to unbonded two-way systems. And then we do want the program to check minimum reinforcement, and we want to include the contribution of pre-stressing in the design. So we want the capacity from pre-stressing to be contributing to the design. I'll generate moment capacities based on design values. So this means that the capacity that the program reports in section 35 of the report is based on user-defined rebar, post-tensioning, and any calculated rebar that is produced by the program. The program is always trying to calculate reinforcement if there's a demand for it. The actual capacity report depends on what the setting is shown here. For the calculation of force necessary to meet precompression, okay, so we're going to consider the calculation for precompression with the presence of drop panels or drop caps. In this case, it doesn't really matter because the slab is flat, so we're going to just produce the required force for precompression based on whatever is the maximum geometric area for any design cut along a span. So we do want to consider this. This is actually a requirement, I think, in ACI 2014. The requirement above doesn't apply, so we'll leave that unchecked. We'll go ahead and select Next. And for span geometry, we'll go ahead and set up our system. So we have 3 spans. Length of 15, 28.5, and then 30. We have a right cantilever, and the cantilever here is 10 feet. Okay, so we also are going to enter our geometry. So we know that the width of all of our spans will be 260 inches, and the height, we said we're going to start with a 7-inch slab. I'll just enter that on the typical row and then enter to move that down. You'll notice if we zoom out here on our image, the datum right now is at the top of the slab, and what that means is that all of our control points for the tendons will be negative below that datum. So a lot of times we recommend that you input a RH value, a reference height value of 7 here, which pushes the slab above the datum, and that means that all the control points will be based on the soffit of the slab to the top. So this is, I think, more inclusive of what is actually shown on a lot of engineering drawings in terms of referencing the CG of the tendons at control points. So we'll leave that as is. I'll go to a top view, so I'm going to use these icons here. We'll go to the top view. We can see we have a datum here, and the multiplier means if we look at this datum, this is actually the left side and this is the right side. So if you can imagine, you're standing here and you're looking this way, here are your arms, and the left side is the left multiplier, so we're taking this multiplier 0.5 times 260, and 130 inches are distributed this way, and then the right multiplier 130 inches are distributed this way. Since it's a 0.5, we're splitting this in half. So you can adjust the distribution of the flange, or the say the two-way slab width, the tributary, to either left or right using these multipliers. This can be input greater than 1 also. So we're going to go ahead, let me go ahead and turn this off. And if I was to input, for example, a 5 here, you can see that this actually gets multiplied by 5, so it's 260 times 5 to this side. So I'll go back and just enter a 0.5. If you enter the full width here, you don't need to enter, these two should sum to 1 typically. If you enter a unit width, which might be more appropriate for like a one-way slab, then you could enter something greater than 1 if you wanted to extrapolate it outward. Okay, so let me go back to a side view of our system. Now for span, actually let's stay on top view. For span 3, this is actually going to be non-prismatic. And what we'll do is we'll select more, and I'm going to add 2 additional segments. So the first segment starts, if I go back to the side view again, and we haven't input any supports yet, so I'll just draw in the support so you can see what I'm referring to. Segment 1 actually starts at the center line. Segment 2, and it goes from center line to this face of the support. So this segment is automatically created. The next segment, so this is, for example, segment 1. Here we don't have a support defined, so these actually both start at 0. But the next segment is where this starts. So this will be 1 input, so I'll call this segment 3. This will be 10 feet. And then segment 4 will also be 10 feet. We're going to say that that opening is within the middle, let's say the middle third of span 3, which is 30 feet. So we'll go here and say that this really starts at 10 feet, and then this segment starts at 20 feet. And we know that we're cutting out half of the flange here, so I'm going to make this 130, and then I'm going to modify the multipliers. This will be 0.1, and we're going to say that this is 0.9. Okay, and we'll go back and say OK, and then say next, and we'll see a top view of this. You can see that the flange gets pushed. So this is 130 inches, and I've shifted it down to this side. Now this should really align. I didn't input the exact values as they should be, so you might have to go back and tweak that. This might actually be like 0.02 and 0.98 depending on what the geometry is. So that's closer to what it would really want to be if you want that to be flush on this edge here. So once the span geometry is entered, maybe rotate that to look something like that. We'll go next. We're going to input lower columns. So I'll say that these columns are 10 feet. We're going to say they're 20 by 22 inch columns. And once I input those columns and I go back to this particular let's say I go back, if you were to go here, this would then be indicative of the actual support widths, this input. So this gets updated automatically. The user doesn't technically have to go back and update that. And you can see there's a segment 1, segment 2, which ends here. This segment 3 actually starts at 10, and segment 4 starts at 20, which is what we had input in the geometry. Okay, so that's our span and support data. We're only going to do bottom supports. You could do top supports. I mean, there's an argument to do top supports when we're checking, for example, service total stress, because if this is just some intermediate floor in the building, you're really going to have probably top columns here. Currently, there's no way to isolate and say for initial stress, check with bottom columns only. For top stress, check with both. So you can tweak stiffness. You can turn off and on columns, in terms of this input to check one versus the other, but it requires 2 runs in order to do that. Okay, the left and right edge, I'll go back to the plan view. Again, remember that this is the left and this is the right. So for 2A slabs, we typically check punching shear at some critical sections away from our columns. And I'll just draw some rectilinear critical sections here that we might, these might be the first critical sections that we check at some distance d/2 away from the face of the column. And if I turn on a wireframe, you can see below, let me turn off the supports. There's an option here for show and hide fixity. So these are our critical sections. If we're looking at one direction, we can clearly identify the type of condition that each column is. So if we're looking at bending, let's say that if we look at this column, and this is the local axes of the column, this might be S, and we'll call this R. And let's say we're bending about S. We know that if we're bending about S in this direction, that this is actually an end condition. So this is end, and if it's an end condition, then it's a 3-sided critical section. We have some centroid for this critical shape, which is not at the column, it's somewhere here to the right of the column. At this, we know that this is interior, right? This is a 4-sided critical section, and this is also interior. This is interior. We know the distance from this column to this slab edge here is greater than 4 times the slab thickness, 4 times h. So this becomes counted as part of this critical section, and this is again a 4-sided, and the same thing here. This is 4-sided. But what's happening out of plane requires the user to provide some input. So if you want the program to check the distance from the column to the edge of slab and determine whether or not that is actually greater than 4 times h to either side, then you have to mark this as exterior. So this is really an interior frame, but we have a condition here where we have a cutout, but it's not near a column. So in reality, we could just say, well, this is really an interior frame line, and we mark it as interior to either side. And what that does is it just simply suppresses the check for determining whether that column is near the slab or not. If it is near the slab, then the program can correctly categorize the column for bending out of plane, so about the r-axis. So that's what these 2 options are here. They help categorize the column and how the program checks a column for punching shear. So we'll leave them as interior. I'll go ahead and say next. We know, I'll turn the supports back on. The support fixity currently is fixed. So 1 is fixed, 2 is a roller, or excuse me, 2 is pinned, 3 is a roller. Right now we have lower column near, which is this side. This is 1 on each of these, 1, 1, 1, and 1. And then lower column far is also 1, so this is 1, which again equals fixed for all of these. So it's fixed. You can modify it again to pinned roller at either end. Okay, that's the fixity condition. The support width, which is taken from the column data, is 22 inches. This just means that at this support number 1, this is 22 inches here. So the actual program, when it determines, moments in that, and you have some moment diagram, it knows where to cut off the moment diagram based on where the face of support is, and that's based on this input here. So we'll leave that as it is. You can modify that. If you deselect this, you could, if you wanted to be conservative in your approach, and maybe you want to take this as 11 in 11, then the program says, well, this support isn't 22, it's actually 11, and half of 11, 5.5, is really the location to the left or center, or to the left or right of the support center line where the cutoff occurs for face of support for moments and shears. So that could also be done. Going next, we're going to add some loads. The loads are pretty intuitive. We have several types of loads that are shown here. To input the load, you can drag and drop into these cells. You can input the second character. So if I type in, for example, a U and a U, there's two uniform loads. I'll just call this all. We're going to just do uniform loading here for everything. Okay, and we'll call this all. And this is live load. And I'll update this to U. And we're going to say that the loading is 20 PSF for dead load, and I'll just use I'll use 75 PSF for live load. Okay, so we'll produce a set of loads that hopefully means that the controlling amount of PT is governed not by precompression but by the allowable stress requirements. If you want the program to skip live load, you can turn this on, and when the live load is applied to different regions on these slabs, you can input a skip factor. So here I'll put 0.75. The program automatically considers the self-weight. If you select no, then you can classify it here as a new classification for the load case. We'll go ahead and use the option to consider self-weight. So we have two loads, 20 and 75 PSF, and those are shown here on the system image. You can see there. We're going to include skipping. We'll go to material. I'm going to use a 5,000 PSI. I want to press enter to update the modulus, or you can override it. The creep coefficient will be 2. This is applied to long-term deflection calculations for the program. And then we're going to say that the stressing, the strength of the concrete at stressing is 3,500. This is usually about 0.7 to 0.75 F prime C. The columns, I'll say, are also 5,000. For the material, we'll use 60 KSI for the yield of the longitudinal reinforcement, and for the top and bottom bars, I'll use number 6 bars. Actually, let's use number 5. This is a 7-inch slab, so we'll use number 5s. We're going to assume shear reinforcement in the form of studs. So the preferred stud diameter will be 0.5, half an inch diameter stud, 60 KSI, and the columns are square, so we're going to use 2 rails per side. We'll go ahead and go to the PT material. So we know we're using unbonded, half-inch diameter unbonded tendons. You can select bonded, which just means that the wobble and friction coefficient and the way the program treats the design and also the minimum reinforcement is different between bonded and unbonded. So typically for a building system of this nature, in the ACI governed zones, we would be using unbonded. So area of the tendon is 0.153. That's for a half-inch diameter tendon. The strength of the tendon is 270 KSI. That's FPU. And we're going to be using the effective force method, which means that we assume a final average force for the cable. So if we look at a diagram, a graph, and this might be, the force in the cable versus the length. And this is the actual force after all losses. If you have a tendon that is a live dead configuration. We might have a tendon that this is actually, we'll say that this is dead and this is live in. We have a tendon that looks like this. This is the loss diagram, and this might, you know, if you look at this delta here, this is usually due to seating. So you lose force when you seat and the tendon is being anchored and stressed, and then that builds up, and then you have losses that occur over the length of the tendon. And if this is the short-term diagram, then the long-term diagram is usually just some offset of this. So if we were to take an average of all of these points, then we might say, well, on average, the force in the cable might be 100, or the stress in the cable after all losses is 175 KSI. So that's what this value is. If we take that and multiply it by this, we get 26.7 kips per tendon. So that's our assumed effective force in the cable for the design. Okay. If you wanted to add base reinforcement to the system, you could do that using this input here. Right now, if I go and just go to a wireframe, I don't have any reinforcement that I've added as user defined, but if I select yes, for example, and let's say I wanted to add mesh reinforcement, I know my first end location will be at span 1, and the fraction of the length of span 1 will be 0, so that's the very end left side. And we're going to input this all the way through, so this will be 1. That means it's the right side of this span, or the cantilever. Bar size we'll say is number 5. Spacing we're going to use is 12 inches, and these will be bottom bars. And the cover is 1. And what happens is the program adds that reinforcement into the system. So we'll rotate this, and graphically the distributed rebar is typically shown here in the graph. I may need to turn the rebar on. Let me go back to this. If we turn this to isolated versus mesh, we're going to do like 6 bars, let's say. Okay, and now these are shown. The mesh rebar graphically is not produced here, but the isolated is shown. So graphically it may not be there, but analytically it is for the mesh. But that allows you to input the minimum reinforcement for user definition of rebar. A lot of times for new designs we're not going to input anything for base reinforcement. So we'll leave that blank for now. The program will design the reinforcement for us in terms of what's needed to meet the design criteria. So for allowable stresses, we're saying that for a two-way PT slab, the sustained and total stress cannot exceed 6 square root of F prime C for tension, and for the initial stress we cannot exceed 3 square root of F prime C. So those are set here. You also have the compressive stress inputs here. These are based on code, so the user can always modify these if you have more stringent requirements. The required precompression that we want to meet is minimum of 125, maximum of 300 for this system, and then we want to balance, let's say, 50 to 90% of the dead load. Okay, that's what our design input will be in terms of the criteria. So there's basically 3 sets of criteria. There is the allowable stresses, and then the minimum precompression and balanced loading, and the program tries to find a suitable design that meets all 3. We'll go next. This is where we dictate the analysis method, or the calculation method for the post-tensioning. And I mentioned earlier we were using effective force method, which is selected here. If you want the program to calculate losses, then we can use the calculated force or number of tendons method, and we input the short-term and long-term loss parameters here and properties, and the program would then calculate this based on the actual losses in the system versus an estimation or an approximation using the force method. The profile of the cables, if I go back to this span, you can see here right now we're set to include for spans 1, 2, and 3 we're using a reverse parabola. So We have inflection points 1, which is the distance from this support to the inflection point for the cable shape. X2 is the distance to, again, the second inflection point, which is usually the bottom of the cable from the soffit of the slab. And then the opposite end, X3, is again the inflection point there. You have other cable profiles that you can use, partial parabola, where this is straight and then it goes into the shape, harped, straight, or extended reverse parabolic. If you wanted to use a simple parabola, then just enter 0 for x1 over L and x3 over L when set to a reverse parabolic shape. Here we're going to use the shape number 1. For the cantilever at the right, we're going to use a straight profile. So we're going to have this just anchored here at the top, and it's just going to go straight to the CG of the slab here. Usually you have a straight or maybe a cantilever down type of a profile for this condition, so we'll just estimate it using the straight. We don't have the option for cantilever down explicitly here unless you leave this set to 1. In that case, the program defaults it to a cantilever down, but we'll simplify it and just say it's a straight shape. The options for tendons here, right now the program by default only includes one tendon, and this is called tendon A. Tendon A always goes from the start to the end over here. So tendon A can be calculated based on some force. Again, the program by default will say how much this force is to meet the criteria, or we can set this to tendon to 0 force, and we can use what are called add tendons. So an example would be, we'll say that this span number 1 is not post-tension. It's an RC span, but we want to post-tension spans 2, 3, and the cantilever. So we cannot do that with tendon A using multiple tendon path, because tendon A always goes from start to end, meaning if I set a force, it's going to be included in span 1. So what we would do is we would use either tendon B or tendon C. These are called add tendons, and tendon B or C can start here, and then you can stress at this end. You can anchor behind this column at some distance, and that distance by default is dictated by this input here. So it's saying that by default for tendons B and C, if they are included in a design, anchor them 0.2 times the span behind the column. So this would be 0.2 times 15, this distance x right here. That can be modified. That's just a default setting. We also want to dictate what the shape of the tendon is. So if you have a column, and I'll blow this up, here's a slab, and we have this tendon that drapes high, and then it gets anchored back here. Well, do we want to follow the shape of the actual curvature of the cable based on its position and geometry and so on, or do we want to just force it to be anchored at the centroid of the slab, which might be this distance 3.5 inches? This would mean there's no induced moment at that location where it's anchored, so it's pretty common to anchor at the centroid of the slab, and that's what we'll do with this cable. Okay, we'll go next. The criteria for cover, we're just going to assume for the tendons we're going to use 1 for the CG defaults. So from the bottom at midspan it's 1, from the top at midspan it's 1, and then at the anchors it's half the depth of the slab. And for the bars in the slab we'll also use 1. So this might be modified just based on standards for your given design, but here we're just going to simplify and say that those are 1. Bar extensions, this is just input telling the program how to cut off bars for minimum requirements and for strength. So this might be thought of as development length for the strength rebar and cutoff lengths for service rebar. If the user wishes to get more get more customized in how the bars are cut off, they can use the curtailment options. So in the curtailment menu, I'll pull this up, we can see that we have different options. ACI 318 has a specific form that cannot be modified. So if you use ACI 318, the program will use these cutoff lengths based on the position and location of the bar, cantilever, exterior, interior span, and based on some allocation of the total area of steel required being allocated to a long bar versus a short bar. If you want to customize this, you would have to select user defined, and then these values become customizable. If you want to use the values that are actually here and propagate those into that table, then we would select the option for adapt, shown here, and this gets basically filled in based on those previous settings. Or you don't have any curtailment requirements, you just use these basic options here for the cutoff lengths. So we'll use none for this for now, and we'll go ahead and say next. And then we have our combinations. We have strength combinations, 2 of those for gravity and also service. So we're going to evaluate sustained load, total load, and then in the initial combination. These are checked against 6 squared of F prime C again for tension, and 0.45 and 0.6 times F prime C for compression, and then this is checked against something different for a special condition when we transfer the force in the system. For strength, we determine and calculate reinforcement necessary to meet these ultimate level requirements. So this affects both the flexural design and also the punching shear design. If you wanted to include lateral loads, you can do this here by again defining 2 additional combinations and including the lateral joint moments in the model. So that's done for lateral loading. We're going to say OK, and then we're going to save the model. Okay, once the model is saved, we're going to execute. So the first thing we need to do is determine the post-tensioning, and we can either use this icon to save and execute analysis or go to execute, and that will produce a set of results in what we call the PT recycling screen. So I'm going to turn the graphs on and move this over. This is currently the design that the program has determined. This is the profile, the shape. And graphically we can see the stress diagrams here. If we look at the total bottom fiber stress, there's very little tension in the system. It's almost fully pre-compressed. We get a little bit of tension here. If we go to the total top fiber condition, we get tension here at the support. If we look at sustained, again, there's absolutely no tension at the top or the bottom, so it's fully pre-compressed. If we look at the last graph, we can see the required forces are these peaks. This is at midspan and at support. This is usually where our maximum stress occurs, so this is where we get these peaks. And the force that we're supplying the slab with is up here. So that covers the required set of, or the required reinforcement or the required post-tensioning in the slab. So looking at the different values now, let me go ahead and close that for a moment. We can see that in tab 1, this is tendon force and height. So we're only using tendon A currently. If I wanted to use tendons B and C, I can adjust by pressing Control and sliding this. I can adjust where they're anchored in the model. I can press Shift and change the stressing end. So this is live, this is dead, live, maybe this is dead. And once you make a change to anything related to tendon extents or to the force or profile, you have to recycle. Now I haven't actually assigned a force to tendons B or C. All I've done was change their position. If I go to B and C, notice that the force is still set to 0. So the program is only assuming that tendon A is active. And it doesn't really matter what the stressing ends are because we're using the force method versus tendon method. We're just assuming the average force along the path of the cable. So if we were to calculate the force, then we would need to change the stressing ends to properly account for those in the calculation of the friction loss and the seating loss. We'll go ahead and recycle. We're forced to recycle only because we made changes to these, but the design is really still the same. It's 560 kips. I'll actually change this to 560. Again, if I make a change, it's asking me to recycle. I'll go and update by recycling. And we have a heads-up display at the top left that kind of shows us the current state of the design. For PT force minimum, 125 psi, we meet the requirement. For PT force max, which was 300 psi, we're actually a little bit over, and that's shown here, 308. This is for the current tendon selected, which is A, but since we're only using A, this is reflected also for all tendons. So this is the summation of force for all tendons and results for all tendons A, B, and C. These are actually set to 0, so this set of force, these results are going to just match, over with these results here, because A is the only tendon active. And we can see again, we have a slightly higher P over A than what we had input in our criteria. So that's reflected here. The balanced dead load is okay. Our balanced loading is roughly 50 in the cantilever up to 90% or 89% at span 1. So this is right on target for min and max balanced loading. For min and max service, we have, or for tension compression service, we have okay and okay. So this is telling us that at sustained and total stress conditions, our stresses are acceptable. And if I go to tab number 4 under total stress, we can see the stress values. This is like a constant in front of square root of f prime c. So the allowable is 6. We're at maximum of 4.1 at this right location of span 2, and then on the opposite side of that joint we're at 3.3. So this we have more room, in other words, here. So we're not maxing out the stress for the total condition. Sustained, we would expect, would be even less because there's less live load. So you saw in the graph, under sustained condition, we're actually fully pre-compressed. These are the tension stresses versus compression stress. And this is our allowable, 6 for tension and 0.45 for compression for sustained, and then this jumps up to 0.6 for sustained. We can also look at initial. The initial stress has to be less than 3 or 0.6 for compression, and here again it's fully pre-compressed. This is all 0 for tension, and we have roughly 0.1, 0.2 for compression, so we're well within the limit. I'll go back over here. So we say, well, what's causing this maximum P over A to be exceeding 300? And if I go to required PT force, tab 3, we can see that the controlling force is actually dictated by load balancing in the cantilever. We need 559 kips in order to maintain the proper load balancing in the cantilever. We only need 227 kips here to meet the P over A requirements. Okay, this is the maximum force needed to meet any P over A along any span. So this is our controlling driver, let's say, for the design. And if I wanted to test this, if I go back and look at this, I say, well, my balanced loading percentage is 50 in that span in the cantilever. If I was to drop this to 500, let's say, and recycle, okay, now the balanced loading minimum is no good. Now this drops below 50. So to meet a minimum of 50% balancing in that cantilever, this has to be 560 kips. And I'll recycle again. And you can see this is interactive. Now we might be able to live with this being 308. So if I went back into the input and changed it from 300 to 308, this would be okay. This is not technically governed by the code. It's just I would say governed more by standard practice and values you would want in a system for pre-compression for a two-way slab. So even at 310 P over A, this design likely would still be acceptable, and we'll go ahead and just exit out of the recycler. Once we exit out of the recycler, then we have the ability to calculate deflections and reinforcement. So exiting out of the recycler takes us into what's called the shell results. And in the shell, we can invoke multiple types of reporting mechanisms. We can look at graphical reports, which shows us several graphs like tendon height geometry, PT force diagrams, stress diagrams, deflection. This includes the presence of cracking and also long-term effects, so using the creep multiplier. So this is the absolute maximum, let's say, deflections you would have under service total or service sustained conditions. And you can see out here on the tip, this considers long-term, we have this deflection on the cantilever of almost half of an inch upward. So this might be cause for concern for design if that is too much deflection. We also show shears and bending moments for different load cases or the combination envelopes. Okay. We also can go into what's called builder sum. Builder sum is a summary, a graphical interface that allows us to look at the results for combinations or the envelope of combinations. So if I select, for example, strength, maximum live load, this is positive lateral because I didn't turn my lateral loading off in the load combinations. Even though there's no lateral loading, it still signals this here. If I select that, I can look at, again, shear diagrams for this particular combo, moment diagrams. Stress diagrams are not produced for strength combinations, so I would have to actually check a diagram for service to get stresses, but we get the same type of diagram for allowable versus top or bottom stress under a given condition, service 2, for example. Reinforcement, we have reinforcement diagrams. To summarize all of this information, if we go back to the envelope, we can produce the summary. And the summary sheet will give us a lot of info related to the design. We have, for example, just an outline, a member elevation showing the spans, showing the shape of the profile, which is scaled based on this vertical scaling of the thickness of the slab. Top rebar and the disposition of the top reinforcement is shown. So 5 number 5s by 4, 5 5s by 11. The actual positioning of the rebar, how do I know where this point starts, for example? That's reported in block 10 of a tabular report. So this is just showing this graphically. Number of layers, the program will check to make sure this bar set fits inside the thickness of the slab. If it doesn't, then the layering would be 2 or 3, meaning you have to provide rebar vertically in layers for a system. This usually is only a problem when you have beams that are narrow in width. The program checks the spacing laterally between bars. The tendon profile, so we show for tendon A, B, and C what the profile is. These first line of data is the CG from the bottom of the slab, and that's indicated by these brown markers here. And then this is the force. So in each span, the force is 560, 560. That's what's shown there. Tendon B and C are blank. We didn't add any of those cables. They were set to 0. We show the force per width so this is 25.85. So if I take this force 560 divided by 260 inches, this is the outcome, 25.85. So on your plans, if this was a uniform direction, we wouldn't technically specify this maybe as 560 kips. We would specify maybe as a range 25.85 kips per foot over the width of the strip. And that's what's shown here. We also show the pre-compression in each span. That's there. And then finally, bottom rebar. So for this slab, we actually don't need any bottom rebar. That's for a two-way slab. Bottom reinforcement, if it's required for strength, then it would be shown here. The cables provide enough strength. And for minimum reinforcement at the bottom, if the stress is less than 2 square root of F prime C or the equivalent in SI, then you don't need bottom reinforcement for ACI. So that's what's happening here. Graphically, we show the required versus provided bars for flexure. We indicate the solution for punching shear. So this first column is okay. We need to reinforce the other 3 columns. And there's a reinforcement table inside of, again, block number 14 in the tabular report. Finally, we show design parameters, material quantities, and if we go to the second page, we show a reflection of the deflections. So we show it graphically and also in the table. Closing builder sum. If we go into this last reporting option in the shell, this is the report generator. This allows us then to produce a tabular report. One such a report might be what I had mentioned earlier for reinforcement, mild steel, and also for punching shear and deflections, for example. I'll create a new report. This will be produced here in Word. This is an RTF file, so we have different blocks of data for reinforcement, punching shear, and deflections. And it's recommended for the user to produce these reports and become familiar with the output shown in those reports. You can also match a report and show that as a Excel file by selecting this option. So it will produce both the Word RTF document and the Excel document using this checkbox. If you have any questions, please contact us at support@adaptsoft.com. Thank you.